So let's continue our study of group homomorphisms. Last video we defined group homomorphisms and looked at various examples of group homomorphisms. I am going to study further now. I am going to start with some basic properties of group homomorphisms. So properties of group homomorphism. Okay, so some of the most important properties are the following. So maybe I will write this as a definition, proposition rather, proposition. Let phi from G to G prime be a group homomorphism. It sends, in other words, phi of AB equals phi of A times phi of B for all AB in G. Then we have two statements. Phi of EG is EG prime. So just to clarify here, E always stands, remember, for our identity element in a group. But here I have two groups, G and G prime. So I am going to be denoting which identity I am talking about by looking at the subscript. E sub G is the identity element of G, E sub G prime is the identity element of G prime. So what I am saying is that in a group homomorphism, the identity element of the first group goes to the identity element of the second group. Further, we have if A belongs to G, if A is an arbitrary element of G, then phi of A inverse, that means I first take the inverse of A and apply phi to it, I get the same answer as first taking image of A and taking the inverse image. Okay, so what, just read this carefully. I first take inverse image, I first take the inverse, then take phi, or I first take the image and then take the inverse image, I get the same answer. So inverse and then phi is same as first phi and then the inverse. So these are the properties of group homomorphisms. So let's prove this. This is very easy. The condition that phi of AB equals phi of A times phi of B guarantees this. That is a powerful condition that guarantees this. Note that EG times EG is EG, right? This is in G. This operation is taking place. This is an equation in G. That is because anything commutes with EG. So in particular, anything when you multiply by EG, you get it back. So in particular, EG times EG is EG. So apply phi to both sides. Okay. Now, because phi is a group homomorphism, phi of EG times phi of EG is phi of EG times phi of EG. Phi of EG times EG is equal to phi of EG. I am not changing the right hand side here. Phi of EG is same as I am keeping it as phi of EG, but the left hand side becomes this because of the group homomorphism property. Okay. Now let's look at this. This is in G prime. This is an equation in G prime. We started with an equation in G, applied phi to it and translated it completely to G prime. So now what does this mean? You have two elements. So you have an element actually in G prime that you want to multiply, you get it back. So we are trying to show that phi of EG is EG prime, but whatever it is, I can multiply by both sides of this by the inverse of phi of EG. What do I get? This is an element of the group G prime. So you have two elements multiplying to this element. They all happen to be the same element, but you can multiply by this element, inverse of this. So phi of EG inverse times phi of EG times phi of EG is phi of EG inverse times phi of EG. right? So that's what we have. When you multiply out, you get this. But then what is this? Because again the group is associative, we can combine these two and that will cancel because that's the inverse of this. So we get phi of Eg on the left hand side. And what is phi of Eg inverse times phi of Eg? This is an element inverse times itself. So this is nothing but Eg prime. This is the property of inverse in a group. Phi of Eg is some element. I am multiplying by its inverse. This is some element in G prime. I am multiplying by its inverse. I get Eg prime. So this proves the first property that I said. So the identity element of the group G maps to the identity element of the group G prime, right? Second property is similar and easy. So let's say that we have already shown that. So we know that A times, so let A be in G, then A times A inverse is Eg, right? This is the definition of inverse. So apply phi to both sides. So phi of A times A inverse is phi of Eg. By part 1 this is already shown to be Eg prime. Phi of Eg is Eg prime. Now the group homomorphism property says that phi of A times phi of A inverse is Eg prime. So phi of A times phi of A inverse is Eg prime. But remember, inverse is the unique element which has the property that phi of A times it is Eg prime. So by definition of inverse, we must have phi of A inverse is phi of A inverse, the whole inverse. Because phi of A, when you multiply with this element here, you get the identity element. So this element must be the inverse of phi of A, which is denoted by phi of A whole inverse. So this is, remember, the second property. Phi of A inverse is phi of A whole inverse. So this proves 2. So the proof is complete. In other words, identity must go to identity under a group homomorphism, inverses must go to inverses. This is useful to keep in mind because it tells you quickly if a map is a group homomorphism or not. If it doesn't send identity element to identity element, it cannot be a group homomorphism. So if you recall, one of the examples that I did in the previous video was sending a function from z to 1 comma minus 1. Phi of A is, let's say, 1 if A is odd, minus 1 if A is even. And I asked you to check that this is not a group homomorphism. That was left as an exercise for you. Now let's do this exercise using the proposition that we proved today. Remember, the other way, if you send even numbers to 1, odd numbers to minus 1, that was a group homomorphism. But if I interchange this, it's not a group homomorphism. In fact, what is the identity element of Z? This is my notation, right? E is always the identity element and I am denoting the group by the subscript. Remember, Z is a group under addition. So the identity element is 0, right? And 0 is even. So under this map, phi of 0 is, because even numbers go to minus 1, phi of 0 is minus 1. But what is if you call this group G prime, what is E G prime? Certainly 1, because this is a group under multiplication with 1 as identity. So the 0 element does not map to the identity element. So phi of Eg, Ez rather, is not equal to Eg prime. So phi is not a So phi is not a group homomorphism. We don't need to check anything more. You simply you simply check that the identity element does not go to the identity element. It cannot be a group homomorphism. Okay, so similarly inverses go to inverses. So however, I want to make a point here. If the identity element goes to the identity element does not mean that it's a group homomorphism. The proposition does not say that if this condition is satisfied, if EG goes to EG prime, it is a group homomorphism. It only says that if you have a group homomorphism, identity element goes to identity element. So neither of these are sufficient conditions for homomorphism. They are only necessary conditions. They must be true, but if they are true, it does not mean that it's a group homomorphism. Okay, so now that we have this, let me define some important subgroups associated to important subgroups associated to a group homomorphism. Okay, so there are two. So let me work now with an arbitrary group homomorphism. Let's say phi from G to G prime is a group homomorphism. So we define two subsets first, and we will check that they are group homomorphisms. We will define two subsets first and check that they are subgroups. So kernel of phi, okay, this is the word kernel of phi, and it is denoted simply by ker phi, is the following. So you define ker phi to be all elements of the group such that phi of A is the identity element of G prime. So this is all elements of the group such that phi of A is EG prime. Exactly the subset of elements which map to EG prime. So, and similarly, so let me define this first. Image of phi, so this is a subset of G, remember, kernel is a subset of G. Image phi, which I will denote by image phi, is the following. Image phi is equal to simply the image of the function phi. So this is just a set theoretic notion. I am taking all elements of G prime. This is inside G prime clearly. This is all elements of G prime which appear as the images of elements of G under phi. So the proposition now is kernel phi is a subgroup of G. It is a subset of G by definition, but in fact it's a subgroup of G, and image phi is a subgroup of G prime. This is true for any group homomorphism so if you start with any group homomorphism phi, kernel is a subgroup of G, image is a subgroup of G prime. What is the proof? It is again fairly straightforward. Let me check one. What is a subgroup? If you recall from a previous video, subgroup is a subset of the group which is closed under multiplication, which has inverses and which has the identity element. Okay, so first of all, is it closed under kernel phi is closed under the binary operation of G. So let's check this. Kernel phi is closed under the binary operation of G, not G prime, of G, because if A and B are in kernel phi, This means phi of A and phi of B are both EG prime. By definition, kernel phi consists of elements which map to the identity of G prime. But then what is phi AB? This is by definition, sorry, not by definition, by the property of a group homomorphism is same as phi of A times phi of B, which is EG prime times EG prime, which is EG prime. So that means AB is in, right, because AB maps to EG prime, so AB is in the kernel phi. So we started with two elements in the kernel and concluded that their product is in the kernel. Kernel phi contains EG. This is very easy, right, because what is phi of EG? This is by the previous proposition, this is EG prime. So that means EG is in kernel phi. Finally, kernel phi is closed under inverses. The third property that we require for a group, subgroup. Is it closed under inverses? Yes, because if A belongs to kernel phi, that means phi of A is EG prime. By definition, it is EG prime. By the previous proposition, phi of A inverse, phi of A inverse is phi of A inverse by the previous proposition, right? And this, so let me write it like this. Phi of A inverse, which by the previous proposition is phi of A inverse, which is EG prime inverse, which is EG prime, right? Phi of A inverse is by the previous proposition inverse of phi of A. Phi of A is EG prime, so it is EG prime inverse. Inverse of identity is itself. Okay, so that means A inverse is in kernel phi. So we have checked three properties. Kernel phi is closed under binary operation of G. It contains the identity element. It contains inverses. So kernel phi is a subgroup of G. Now let's check that image is a subgroup of G. I am going to show that image is a subgroup of G. Similarly, exactly as before, image phi is closed under binary operation of G prime. Right now we are claiming that image phi is a subgroup of G prime, so it must be closed under binary operation of G prime. What are two elements of image phi? If you recall, image phi is phi of A in G. For all elements A of G, we take phi of A. So two elements of image phi would be phi of A times phi of B. Let's say they are both in image phi, but that means phi of A times phi of B by the property of group homomorphism is same as phi of AB, but this is by definition in image phi because this is the image of AB. Product of phi of A and phi of B is the image of AB. So if you start with two things in image phi, their product is in image phi. Image phi contains EG prime. It must contain EG prime in order to be a subgroup, but it does because phi of EG by the previous proposition is EG prime. So EG prime is in the image. Recall again that image is the image of the function. EG prime is the image of an element, so it is contained in the image. It is a set theoretic image. Image phi is closed under inverses. This is also easy. Let's say phi of A belongs to image phi. Let's say phi of A belongs to image phi. Then what is phi of A whole inverse? By the previous proposition, this is same as phi of A inverse, right? Phi of A whole inverse is phi of A inverse, but phi of A inverse again is by definition an element of the image because it is image of A inverse. So image phi is a subgroup So this proves the proposition. So we have shown that kernel and image are subgroups of G and G prime. So this is an important, these are two important subgroups attached to any group homomorphism. So it's a good exercise now for you to work out the kernel and images in all the previous examples that we discussed of group homomorphisms. I won't discuss in all the examples, but if you consider the map from Z to Z, phi of A being NA, so we have fixed N. This is the first example of a group homomorphism that we studied. You fix an integer n and send an integer A to n times A. The kernel of phi is all integers such that NA is 0, because 0 is the identity element of Z, but this is precisely 0. So the kernel is just 0. Remember, kernel being a subgroup of the group contains the 0 element always. So in this case it is exactly the 0 element. So this is in a subgroup of the first Z. What is image of Z? Phi. This is all NA where A is in Z, and this is precisely the group NZ that we discussed, subgroup of Z obtained by multiples of N. So this is a subgroup. And if you take the determinant homomorphism from G ln R to R star, what is the kernel of this? So remember, phi of A is determinant of A. Kernel of A is the set of matrices in G ln R such that phi of A, which is the determinant of A, is 1. So this is a subgroup by the previous proposition. This is called the special linear group, denoted SLNR. Okay, GLNR is called the general linear group. Special linear group is the group of invertible elements with determinant 1. That is the kernel. What is the image of phi? Image of phi is the set of real numbers which are obtained as determinant of A for an invertible matrix. So image consists of all determinants as you vary the invertible matrix in GLNR. What is this? It's certainly a subgroup of, by the previous proposition, it is a subgroup of the multiplicative group of non-zero real numbers. But I claim in fact that it is all of non-zero real numbers. Why? I claim that image of the determinant map is all of non-zero real numbers. In other words, given a non-zero real number R, let's say, there exists an invertible real n by n matrix A such that determinant of A is R. Not that if I show this, then I have justified saying that image of phi is R star, because if there is such a matrix, it is in GLNR. So A is in GLNR. That is to say, it is an invertible real n by n matrix and its determinant is R. So R would be in the image. So if I want to show image of phi is R star, I need to verify this. But what is such a matrix? I simply can take I'll take a diagonal matrix I'll put one R in the first left hand side position and I'll take ones everywhere. I'll take one everywhere else on the diagonal, zeros off the diagonal. This is certainly an invertible matrix because its determinant is R and R is non-zero. It's an invertible matrix, it is size n by n, it has real entries. Okay, so this matrix will have determinant because determinant of a diagonal matrix is the product of diagonal entries, determinant of A is R. Okay, so the image of the determinant homomorphism is all real number, non-zero real numbers. Of course, we want non-zero real numbers. Just one more example I want to do. This is also something we discussed in the previous video. If you take G is an arbitrary group, fix an element of G and consider group homomorphism from the integers to the group by sending n to a power n. Okay, this is a group homomorphism was something we checked earlier. What is the kernel of phi? This is all integers such that phi of A, in this case a power n, is identity of G. Okay, this is a subgroup of Z. Okay, this is a subgroup of Z. So this is all integers such that a power n is identity, is a subgroup of Z. What is the image of phi? This is a power n. So remember, this is phi power n as n varies over integers, right? This is by definition image of phi. But what is phi power n? This is just a power n as n varies over integers. In other words, this is just a minus 3, a minus 2, a minus 1, a 0, which is e.g., a squared. If you recall and if you remember now from a previous video, we gave a name for this group. This is simply the subgroup generated by A. This is the subgroup generated by image of phi is the subgroup generated by A. Let's look at kernel slightly more carefully. So now, what is kernel of the same example? So in this example, what is kernel of phi? So kernel of phi, as I wrote earlier, is all integers such that a power n equals eg. And if you recall again from a previous video, we have already classified all the subgroups of the integers. What are they? Recall, we earlier classified, so remember this is a subgroup of Z. We already classified all subgroups of, what are they? They are of the form they are multiples of a fixed integer. So I have already used n and a here, so I'm going to use bz, right? They are of the form bz, bz being all multiples of a fixed b. So bz is bn, where n varies over. So they are of the form bz, where bz is this. So every subgroup of integers is like this. So in particular, kernel also is like this. So in our example, kernel phi being a subgroup of Z is of the form kernel phi is bz for some integer In fact, b is a non-negative integer. See, if you go back and see the video where we classified subgroups of Z, they are of the form Bz for a non-negative B. We can always, okay, so I don't want to repeat the proof, but we first rule out the case that it is a 0 subgroup, in which case it is of the form 0 times Z. Otherwise, there are some numbers in it, non-zero numbers, hence there must be some positive number in it, and we take the smallest positive number and show that all elements of the subgroup are multiples of it. So B is either 0 or positive. So now this B is actually something that you are familiar with. B as an exercise, note that B is nothing but the order of A. Recall that from before, what is order of A? So we have two possibilities. So what is order of A? We first look at multiples of A. So we look at E, A squared, A cubed. We keep looking at this. You will never hit E again, the identity element, or you will hit E somewhere. So it is the first place where you hit E if you hit E. So order of A has two possibilities. It's is either, okay, so maybe I should write it like this. If A power n is E for some positive integer n, then the order of A is the smallest positive integer m such that A power m is E. So this is such that. Okay, so S dot T always stands for such that. So if A power n is identity for some positive integer n, I'm going to simply look at this least positive integer which has that property. If A power n is not equal to E for any positive integer n, then I will simply define order of A to be infinity. And now I claim that looking at the map, the group homomorphism which sends integer n to A power n in a group G, we noted the kernel is of the form Bz. It is all multiples of B. So kernel of, remember, phi is all integers n such that A power n is identity. And we saw that it is Bz for some integer which is non-negative. So it's either 0, in which case kernel phi is 0, right? In kernel phi is the 0 set, and in this case A power n cannot be equal to A for any positive integer. So order of A is infinity. So actually I should not say this. So this is not right, right? B is nothing but the order of A is not quite true. B is related, I should write B is related to the order of A. If B is 0, then order of A is infinity. If B is not 0, so B is positive, then kernel of phi is Bz, and now order of A is actually B. Sorry. So in this case order of A is B, because remember kernel is Bz and B is positive. So the smallest positive integer such that a power n is E is B. So order of A is B. So if the kernel of this map is 0, if kernel of this map is 0, then order of A is infinity, and kernel of this map is non-zero, then order is equal to the generator of the group. So B is related to the order of it. Okay. So these are some of the properties of group homomorphisms, and I'm going to stop here in this video, and in the next video I'm going to talk about, so in this video we have looked at basic properties of group homomorphisms, namely that they send identity element to the identity element, inverses to inverses. We looked at two very important groups associated to a group homomorphism, namely the kernel and the image, and we worked out what these are in some of the examples of group homomorphisms that we looked at. In the next video I will continue my study of group homomorphisms and define isomorphisms of groups. Thank you.